So now, it's amazing. It's lots of relationships. It's true for any irreducible representation. And it's not obvious, how do you use this intelligently, because it seems to say that I'm supposed to have an explicit representation. Because whenever I write this indices, it says I've chosen my coordinates in which I've written this representation mu. It's a bunch of numbers with square roots of 3 and God knows what, because that's obtained by going to unitary representation. That's amazing that matrices will satisfy this, but it looks like lots of work to use it. Then the next amazing thing happens, which is realized that the simplest possible invariant under the group, which is a trace of a matrix, suffices. So I don't need to have all this explicit d mu nu matrices with 1,000 things. I can just their diagonal parts summed, and that I find surprising. That turns out to suffice. Why do I find it surprising? When you're given some matrix, obviously the diagonal summed of the matrix is invariant under similarity transformations. So this is a Greek word, but any educated person in 19th century had Latin and Greek as part of their education. So they all use this as a good German word, character. And that means exactly what you know it to mean, something that's specific to a person, in this case, an object like a matrix. And technically it's defined as saying if I have a group element and some representation that I give a name to, it doesn't have to be reducible, but so alpha can be just said, I'm using triangle, I'm flipping it around, and I'm not using 3 billiard balls and permuting them. So these are different representations. Both of them are reducible. If I just take the representation alpha, a matrix representation of the element G, and I sum its elements, then I have the following property of this. I'm allowed to take trace and multiply it by unity of the same dimension. This is a square matrix. And I can write the unity. So this is just unity. Then if I put indices in definition of the trace, I realize this is cyclically symmetric. So I can write this as a trace of U matrix multiplying the representation alpha G. So character has a property that it doesn't care about what coordinates I use, because it's the same number no matter what frame I measure it in. Now, from your algebra, you also remember that if I have a determinant of the same object, product of 3 matrices, I can write it as a product. And in this particular case, this is 1. But even if it's a general similarity transformation, these two guys would cancel. So there are lots of invariants. Here are 2 invariants of that you can get from matrix. You can look at trace of the square, right? You have a matrix, you can square it. You're allowed to do that. But that turns out not to be trace of d squared. That's almost never true. Sometimes it is, but usually it's not. And when you think about it and you use the theorem which we already used with Cayley-Hamilton, there are, D invariants for matrix D of dimension D cross D. So it's not at all obvious that it would suffice to just look at the first of these invariants, which is the trace of the determinant, and not traces of its squares, etc., to fully characterize your group, your representation. Why is one good enough? So that I find miraculous, but it is. So that's why one chooses character. One wants to characterize a group in such a way that it doesn't depend on coordinate choices. Now, this seems a huge simplification of what you started with, because your orthogonality relationship was for full matrices, and you're going to replace each one of them just by a number. How can that be good? Miraculously, it turns out that's good enough. But before we establish this, there's another fact which is very important.